Suppose electrons enter a uniform electric field midway between two plates at an angle theta 0 to the horizontal as shown in the figure. The path is symmetrical so that they leave at the same angle theta 0 and just barely miss the top plate. Part A, what is theta 0? Ignoring the fringing field. Your first reaction to this problem might be panic. Let's not. The point of this problem is a reminder that even though we have added a brand new force into our repertoire, that of the electric force, the methods by which we approach force problems are in fact the same. The most important phrase in the setup of this problem is found here. Uniform electric field. We know that any electric field results in an electric force. If we have a uniform electric field, we thereby have a uniform force, and that is something that we dealt with in great detail back in the first portion of this course. The condition we found under a uniform force of gravity was known as projectile motion. This problem is projectile motion. The only difference between this problem and problems we dealt with back in Chapter 3, known as projectile motion, is that the source of the force, and thereby the constant acceleration, is now electrical rather than gravitational. The realization of this principle is to recognize that as far as electrical forces are concerned, the total force one receives is equal to the charge of the particle in question times the strength of the field in which you find yourself. Once we understand the amount of force, Newton's third law still says that F is equal to ma, and so the quantity QE that tells us how strong is the electrical force is equal to ma, and therefore the acceleration in this problem is equal to QE divided by the mass of the particle experiencing the force. The expression that we just derived is a scalar expression telling the magnitude of the acceleration. If we want to make this into a vector expression, we're going to need to have a unit vector, and we can see that the acceleration is downward between these two plates. At this point, hopefully the problem has become quite clear. This is a projectile motion problem in which the acceleration is no longer 9.8 meters per second squared downward, but is that amount downward. The projectile motion problem at hand falls under the basic category of definition of success, in that we need to figure out what adjustable angle theta 0 will result in the trajectory that we desire, and that is the trajectory that is shown on the screen. The singular interesting aspect of this trajectory is found here at the peak of the trajectory. We recognize that that location is x of 3 centimeter or 0.03 meters, and that location has a y of half a centimeter or 0.005 meter. For simplicity in this problem, I will be referring to this as the midpoint of the motion, and those numerical values I'll be referring to as x with a subscript m for midpoint and y with a subscript m for midpoint. Our task at hand is to set up conditions so that the maximum height of the projectile is achieved at xm, ym. Thus, our definition of success for this problem is going to be that x should be equal to the midpoint when y is equal to the midpoint. If we had an equation that related x to y directly for our projectile, we would simply use that equation. However, we don't. We find that there are no x's in the y equations and there are no y's in the x equations. In fact, there is one and only one variable that is found both in the x equations and in the y equations, and that variable is t. So what we will need to do is assure that the maximum of the projectile is defined using t as an intermediate variable to get between the y's and the x's. Let me be the first to admit that this problem is somewhat difficult algebraically, even though conceptually we have completely finished the setup of the problem. If it took you several times with the algebra to get this right, don't feel bad. It took me several times to find a way to set the algebra in a clean, neat manner. Let's begin that process. I'm going to write 3 sets of conditions that will allow us to get from the concept that the projectile follows the trajectory shown in the diagram and the realization in terms of equations. And I'm going to write down 3 conditions in order to allow this to happen. The first one is that v sub y must be equal to 0 at the maximum of the trajectory, and so v sub y should be equal to 0 when y is at its max. This is the very standard condition for defining the maximum height of any projectile, saying that is the y when vy equals 0. That's perfectly clean. However, we don't yet have time involved, so we're going to have to use time as a stepping stone to get between the 2 results. In that case, we're going to require that vy equals 0 at a particular time, and we're going to call this t with a subscript m. So far we've only dealt with the y dimension and we've ignored the x dimension entirely. In order to finish the problem, we're going to have to require that x equals the midpoint at the same time as y does. Each one of these 3 expressions corresponds very directly to one of the 3 equations that we use to describe projectile or constant acceleration motion, which this problem really is at its essence. Let's begin at the left and talk about the vy equation. That equation takes this form. Vy squared is v0y squared minus 2g. Let's define this quantity here to be like g. So we'll call it g in our equations. We'll recognize that it's not 9.8. It's q times the electric field over m, but that's okay. We'll still use the familiar symbol g just to make the problem look like we're used to. So this will be minus 2g times y minus y0. Plugging in that y0 would be 0 and vy is required to be 0, we're going to come up with an expression that tells us that v0 squared sine squared of theta shall be equal to twice g times y max. That is the result of the first of our 3 conditions necessary to force the projectile to follow the trajectory shown. In order to deal with the second condition, we need to come up with a relationship between vy and t. This is vy is v0y minus g times t, where again g is the special format. Using the fact that vy is required to be 0 and t should be t subscript m, we will find that v0 sine theta is equal to g times t max. Finally, we need to deal with the xt relation to get the third of our 3 equations necessary to solve the problem. In that case, the x versus time relation is that x is equal to x0 plus v0x times t. And this one, partly because I know the necessary route to solution, I'm going to solve for v0 times the cos of theta, and that will yield the result v0 cos theta is equal to x mid divided by t. These are 3 equations in 3 unknowns. First, I wish to consider the red and the green equations, which we're going to combine together. We're going to combine them by taking the ratio between the 2 equations so as to cancel the factor v0. The left-hand side of the equal sign will show sine over cosine, which will be tangent of theta, and the right-hand side will be g tm divided by x over tm. We'll also combine the center equation with the left equation. So what we're going to do is we're going to square the green equation, telling us that v0 squared sine squared is g squared time squared. And then we find that the g squared time squared from the equation on the right is related to the right-hand side of the equation on the left. This gives us the result that 2g times y mid is equal to g squared t squared, which we can solve for t squared, yielding twice y at the midpoint over g. Light shines at the end of the tunnel. We will now be able to take this expression for t squared and place it into the result we got by combining the right-hand two equations, and that will give us a single equation for tangent of theta. Tangent of theta is going to be equal to g over x mid times twice y mid over g. Quite shockingly, the g that was the only part of this problem that depends upon electricity actually cancels away, telling us that the tangent of theta is twice y maximum divided by x at the midpoint. Putting in numbers, the inverse tangent of the right-hand side, I'm going to have that theta is equal to 18.43 degrees, and we have just solved an electrical problem by recognizing that even though the force comes from an electric field, if you have a region with a constant force, the motion is a projectile, just like in the days of Galileo.